Hi, my name is Phil Tremblay. I've been working at Maya HTT since 1998. My presentation is entitled Spacecraft Model-Based System Testing, Correlation of Test and Simulation. The RADARSAT Constellation Mission, or RCM, consists of a trio of Earth observation satellites. Maya HTT was responsible for the structural design and for the structural simulation of the bus and the spacecraft. These were launched in June 2019 atop a Falcon 9 rocket. Engineers are often asked, how do you know that your analysis model is accurate? The answer depends on the structure's heritage, the team's experience, as well as its skill in modeling complex assemblies. In the case of spacecraft systems, the loads are derived from coupled launcher spacecraft simulations, and hence the spacecraft model must be accurate. It's often required to integrate dynamic testing into the development plan on either a prototype, the first flight structure, or a combination of both. Next, you need to prescribe a cost-effective dynamic test. If the test article is the flight structure, the test must be quickly performed with as little instrumentation as possible. Next comes the question, how do you compare simulation and test? Well, you need to define goals or requirements for the quantitative correlation of the target modes. And we also need to know how to implement these in the software. Finally, if the correlation requirements aren't met, we need to update the model to align it with reality. Here, the engineer's knowledge is leveraged to guide the software in determining the changes to the FEM. SimCenter 3D FE model correlation encourages a process and offers tools that help answer these questions, starting with pretest, which ensures test quality and helps to speed up the test setup by determining sensor and exciter locations and directions, which are shared with a test engineer. As the test is carried out, we begin evaluating the correlation with analysis. Often many sets of test data are generated. Finally, model updating can be performed. The goal of the RCM modal test was to produce an updated spacecraft FEM for Falcon 9 couple loads analysis. In the absence of fidelity requirements, we propose the following goals for correlation of the target modes using the updated FEM. Cross-orthogonality, diagonals above 0.8 and off-diagonals below 0.2, as well as a frequency difference smaller than 5%. The target modes were the fundamental spacecraft lateral and thrust modes, which contain lots of effective mass and generate high stresses. Secondary spacecraft lateral modes, and fundamental SAR antenna modes. The SAR antennas are the two large structures or panels on each side of the spacecraft in the stowed configuration. Next, we define the locations and orientations of the sensors or accelerometers to distinguish the target modes. There are locations at which measurements are mandatory for contractual or technical reasons. These define so-called initial sensors. Optionally, we can add locations at which we expect large displacements that result in good shape animations. We then define candidate locations and directions. We filter out degrees of freedom with little response and define a geometrically distributed subset of accessible locations. In some areas, like on the interface adapter, it's difficult to align sensors with the global axis, and so the software automatically calculates the normal direction. The maximum off-diagonal modal assurance criteria algorithm, or MODMAC, takes the initial sensors and sequentially adds candidates until the AutoMAC matrix off-diagonal terms are below a user-defined threshold. Next, we need to define suitable locations at which the structure can be excited. Exciter candidates are taken from the externally accessible sensors. In order to reduce the number of exciters, we instruct the code to consider off-axis rotations of 30 or 45 degrees. The normal mode indicator function algorithm, or NMIF, determines the fewest possible degrees of freedom to excite the target modes. For large structures like the spacecraft, which contain many structural joints, we increase the damping ratio and reduce the NMIF threshold. Next, we need to define a wireframe which connects the sensors and allows the test engineer to visualize the test and analysis mode shapes. A wireframe can be defined automatically using an algorithm we provide, manually, for example, by graphically selecting nodes, or a combination of both techniques. It's also possible to automatically add a denser visualization wireframe which allows for the analysis shapes to be better understood by the test engineer. The test analysis model, consisting of 125 uniaxial sensors, 2 exciters, a wireframe, and the analysis modes reduced to the sensor degrees of freedom, was sent to the test engineer. It's always expected the test engineer may need to modify the instrumentation, so, for example, to move an exciter, in order to measure quality data suitable for shape extraction. There were over 40 different measurements done during the RCM modal test, with different input signals, force levels, stingers, exciter locations, and active sensors. Given the amount of back and forth during and after test, it's essential that the interface between test and simulation be as seamless as possible. It's of course necessary to support legacy data formats such as the universal file. However, the increasing demands on data exchange can be better achieved via dedicated native formats. The normal modes of the large spacecraft FEM, consisting of over 1.1 million elements and 1.5 million nodes, were correlated with the shapes from the tests that displayed the best data quality. Sensors were added by the test engineer at the interface plate between the adapter and the concrete floor, as we were concerned with the effect of the floor and the underlying soil on the spacecraft dynamics. SimCenter Nastran Gaussian reduction was used to generate a reduced mass matrix at the equivalent sensor degrees of freedom. Orthogonality between the test and analysis mode shapes can be assessed via the matrix plots, as well as the automatically generated mode pairs. A value of 1 indicates perfect alignment, whereas 0 indicates perfect orthogonality. Model Assurance Criteria, or MAC, is a scalar measure that indicates the degree of agreement between reference and work mode shapes. A value of 1 indicates perfect correlation. In order to qualitatively assess the shape correlation for any mode pair, you can select a cell in the matrix and view the associated shape displays or animations. It's possible to identify which sensor degrees of freedom contribute to a poor MAC value and automatically remove them from the sensor set. On the left, the original MAC matrix. Selecting a cell which we want improvement, and then defining the target MAC value, the software removes as many degrees of freedom as required to achieve the target, and we obtain an updated MAC matrix on the. Whether or not the degrees of freedom should be removed is an interesting question. A faulty sensor is an obvious candidate for removal. In this example, however, we've removed 7 sensors to help distinguish 2 modes that were much closer in test than in the simulation. It's been suggested that small change in the length of the shape vector could be justifiable. Once you've established a degree of correlation between test and analysis, you may need to improve the correlation by updating the FEM. Using engineering judgment, you define design variables that are allowed to change. These can be material properties like Young's modulus or physical properties like shell thickness. Let's look at this sensitivity-based process in detail. First, you need to define a Solution 200 model update solution, which simply computes the sensitivities. You define degrees of freedom for reduction, which can be either modal or physical. The latter is a Gaussian reduction. You then create a model update solution process, which uses the SOL 200 model update solution as work, and the test solution as reference. You define the targets to use in the optimization. These should be the frequencies or shape metrics for the target modes. You can define global or individual weights, modify the design variable bounds, and then select one of the 3 optimizers. Since the SOL 200 sensitivities are linear, they must be recomputed. You resolve the Nastran SOL 200 model update solution with the updated design variables, refresh the model update, and optimize once more. Finally, you update the FEM. Some key features of the model update process include defining a model reduction in the first step, which allows the optimizer to quickly solve the reduced dynamic model using the updated design variables at each iteration. Mode shape targets are based on MAC or on cross-orthogonality. This allows you to converge on your specific shape correlation goals. Optimization targets can be the mode frequencies or the frequencies and shapes of your target modes. This allows you to also converge on your frequency difference correlation goals. You can manage your design variables by freezing them, manually modifying them, or by changing their upper and lower bounds. Updating the FEM means updating the SimCenter 3D FEM part. which can be leveraged in any number of simulation parts and multiphysics solutions. There is no external file handling required. Now the tricky part. What in the FEM to update? Much of the uncertainty in the FEM stiffness comes from structural interfaces like bolted joints. These are complex nonlinear assemblies which behave linearly when properly designed. There are more and more options to simulate them, for example, solid models of bolts and washers with preload, contact, glue. On the other hand, simple and traditional rigid element spring combinations provide solution efficiency since contacts don't need to be established, and since really dense 3D meshes aren't required. These also provide the ability to optimize the stiffness in the model update process. If you know you're going to perform an update on your FEM, you can define interface elements that can be tuned, like springs or beams. You can also define meshes around joint locations to which you assign special materials, the properties of which you can tune. There's overhead in defining these material and physical properties and meshes that will be used to update the FEM. FEM updating may require a significant number of design variables, for example, if you have many joints or if you have many different layups. So several hundred design variables aren't impossible. It's important to be able to quickly define these design variables, and tools exist that allow you to select one or more material and physical property tables and then assign the required fields such as area, Young's modulus, etc. that you want to use in your design variables. In the case of the RCM FEM, the following structural joints were specifically identified for updating. The SAR antenna cup cones for deployment, the discrete interfaces between the bottom of the bus and the interface adapter, the contact area between the interface adapter and the payload attachment fitting, joints between the test interface plate and the concrete floor. We developed a 3D FEM of a region of the concrete floor below which the soil was modeled using spring elements. The tables show the properties which we assumed to define the materials. This provided a prediction of the drop in frequency for the fundamental lateral and thrust modes, all of which exhibit significant effective mass. An equivalent 2-degree freedom method was identified, which allowed us to predict the frequency shifts using a simple spreadsheet. Aside from the higher than expected test analysis frequency difference for the fundamental modes, a strong indication of soil participation was the unusually high damping that we measured. The correlation and updating effort was complicated by the floor dynamics. Substantial analysis time would have been saved had a seismic block been used, which on the other hand would have had significant cost and schedule implications. The deployable solar array FEM was updated by the contractor, and we also added air mass in the spacecraft FEM. The final correlation metrics are shown here. We achieved better than 5% frequency difference for all the target modes, which are shown with yellow shading. In terms of cross-orthogonality, we've had one diagonal value below 0.8 and 3 off diagonals above 0.2. The following simulations were performed on the updated FEM. Notched harmonic base excitation to define the notches and predict the response of the spacecraft during the protoflight qualification sign test. Thermoelastic distortion from map steady state and transient simulations. Vibroacoustic simulations using the Falcon 9 acoustic field, and handling and access simulations. Thank you very much for your attention.